스노우매직으로 매핑을 해봤습니다. 이렇게 매핑을 했더니 당연히 되는 게 있고 안 되는 게 있습니다. 요거를 그림 50도로 보고 뒤에서 한번 다시 보시는데, 예를 들어서 먼저 보시면, 예를 들어서 지금 보시는 것처럼 한약 처방 당연히 스노우매드에 없습니다. 그리고 곤초명도 없습니다. 없냐? 있긴 있는데 몇 개만 있습니다. 그러면 저희가 설진, 렉진 이런 게 있을까요? 없습니다. 그런데 재밌는 건 스노우매드에 유사한 용어가 있습니다. 유사한 용어가 있습니다. 그럼 이걸 어떻게 처리할 것이냐 때문에 저희가 계속 작업을 진행했다 보시면 되고요. 그래서 이렇게 저희가 구조도를 나눴습니다. 온톨로지 전문가들과 함께 나누어서 의과, 안과 동일한 용어가 있고요. 그러니까 컨벤셔널한 것과 트랜지셔널에서 같은 게 있고 다른 게 있으니 이걸 쭉 쪼갰습니다. 이렇게 쪼갠 다음에 이거를 갖다가 스노우매드에다 다시 한번 매핑을 할 때 그 전에 우선 우리 지금 그 보건의료 정보원에서 말하는 EMR 인증제에 들어가는 기준에 맞춰서 요 앞서 말씀드린 인증 요소가 잘 들어갈 수 있도록 다 확인을 먼저 했습니다. 요 작업을 거친 다음에 이렇게 데이터베이스를 다시 한번 만들었다, 이렇게 이해해 주시면 되겠습니다. 요 그림을 보시면 간단합니다. 기본적으로 오른쪽은 처방이고 왼쪽은 저희가 인터벤션에 대한 부분이 되겠는데, 저희가 이게 대중소 분류로 나누어서 각각의 개념을 잡아넣어서 넣었다고 보시면 되겠습니다. 한약이 조금 더 쉬우실 텐데요. 한약에서 제일 문제가 되는 건 한약의 처방명이 무엇이냐를 먼저 인식하는 겁니다. 그런데 문제는 저희가 똑같은 한약 처방이 다른 의미를 가질 수가 있기 때문에 요거를 레퍼런스 D를 뒤에 붙이고 효능과 그리고 제형을 가지고서 저희가 세 분류를 넣었다, 이렇게 보시면 되겠습니다. 그럼에도 불구하고 사용법에 따라서 이 목적에 달할 수 있기 때문에 요거를 각각 뒤에다 정보화해서 붙일 수 있도록 구성을 했다, 이렇게 봐주시면 되겠습니다. 이런 작업을 거쳐서 교육 작업까지 진행을 했고요. 해놓고 나니까 이게 진짜로 의료기관에 쓸 수 있는지가 궁금했던 겁니다. 그래서 이 작업을 각각 병원에다 적용하는 것을 사업을 올해째 3년째 하고 있습니다. 두 번 또 진행한 경우가, 첫 번째는 병원, 지금 보시는 건 한의원에 했던 거고요. 한의원에서는 어렵지만 힘들지만 하면 데이터가 되고 환자랑 정보를 나누기 좋을 것 같아서 긍정적이다 라는 답을 좀 받았고요. 한의원의 한방병원에서는 기존에 있는 EMR 시스템에다가 정보 체계를 넣으면 좀 더 잘 작동되겠다, 이런 정도까지 저희가 반응을 볼 수 있었습니다. 이게 지금 저희가 마지막 슬라이드인데요. 제가 말씀드리고 싶은 내용이 여기 다 들어있습니다. 한마디로 말씀드리면 우리 한의의료진료가 한의약 RWD가 나오는 건 우리 한의사 선생님들이 또는 한의의료에 참여하고 있는 여러 직종에서 함께 데이터를 산출해야 됩니다. 이 산출하는 데이터가 모였을 때 가비지되지 않으려면 애초부터 처음부터 잘라야 됩니다. 이렇게 데이터를 뜯어낼 때 혼선이 되지 않으려면 만들 때 제대로 만들어야 된다. 다만 요즘 시대가 어느 시대인데 LLM으로 처리하면 됩니다. 그런데 LLM으로도 처리를 하려고 하더라도 최소한의 라인은 잡혀 있어야 되기 때문에 저희가 도구를 만들었다고 생각하시면 쉽습니다. 다만 의료기관의 모든 도구를 만든다거나 모든 데이터를 제공할 필요는 없다고 판단을 하고 있고요. 저희 가장 중요한 건 변증 모형, 그리고 진단에 대한 판단, 한의사의 판단, 그리고 중재와 한약에 대한 정보를 체계적으로 만드는 거, 앞서 보이는 것 같습니다. 그럼 이렇게 되면 기본적으로 의료기관의 데이터는 모두 쌓이되 이것이 바깥으로 빠져나오는 모델은 앞서 우리 신수용 소장님 말씀드린 그런 모델을 동일하게 생각하고 있습니다. 암세터 모델도 같은 모델이고요. 이렇게 모아진 것들을 일단은 병원에서 활용하실 때 필요할 경우는 상호 운용할 수 있도록, 그래서 저희가 인터오퍼러빌리티를 확보한다, 이렇게 보시면 되겠습니다. 현재로서는 마이너스웨이, 마이차트에 연계할 수 있는 방안을 좀 확보를 하고 있고, KRCDI에 확보하는 방안도 이렇게 하고 있다고 보시면 되겠습니다. 이를 통해서 결과적으로는 우리 한의진료에서 나오는 정보가 하나의 틀로 만들어진 다음에 다른 사람이 볼 수도 있고 연구를 할 수도 있고 하는 작업이 모두 가능할 것이라 생각됩니다. 아마 조금 더 디테일한 내용들은 언젠가 다시 한번 설명드리고, 그리고 실제로는 저희가 API 작업이 끝나고 나면 한약지정원에서 제공하는 일이 올해 말 아니면 내년 초에는 저희가 일단 1차 안을 좀 제공할 예정이 있습니다. 시간이 좀 짧아서 이것으로 발표 마치도록 하겠습니다. 감사합니다.
네, 고맙습니다. 보건의료 데이터 상호 운용성 확보를 위한 한의학 용어 표준화뿐만 아니라 빅데이터 구축 전략에 대해서 보다 자세하게 설명을 해주셨는데요. 소개해주신 서병관 단장님께 다시 한번 감사 말씀드리겠습니다. 네, 그럼 이어서 두 번째 발표로 넘어가 보도록 하겠습니다. 두 번째 발표는 AI와 빅데이터가 일본 전통의학의 미래를 어떻게 바꾸는가라는 주제인데요. 테츠히로 요시노 게이오 기주쿠대학교 의학부 칸포 의학센터 조교수님께서 발표해 주시겠습니다. 여러분 큰 박수 부탁드리겠습니다.
안녕하십니까. 준슈소 박사합니다. Good afternoon, everyone. My name is Tetsuhiro Yoshino from Keio University School of Medicine in Japan. Alright, maybe some of you have to wear the translation machine. I know the English translation was quite good, so the Korean translation should be very good. So please prepare for your ear. Thank you. So today I am very excited to talk about our research titled From Anecdote to Algorithm, how AI and big data are shaping the future of traditional Japanese medicine. And actually, traditional Japanese medicine is pronounced in Kanpo in Japan. And actually, when we say Kanpo, it's kind of like Hanban in Korean. So it's very confusing. But my Kanpo is Japanese medicine, Japanese style medicine. So please know about that. Right. So first, let me briefly introduce myself. Maybe most of you do not know myself and the unique framework of the Japanese medical system. Thank you. Thank you. So, in Japan, there is only one type of medical license for physicians. So we physicians all study conventional biomedicine in medical school. And for example, I graduated medical school in 2008, and I first trained as an internist and board certified as an internist in 2011, and finished advanced training about internal medicine in 2015. And after that, I choose to subspecialize in Kanpo medicine, traditional medicine, and this is the standard path for becoming a traditional medicine specialist in Japan. And it is also important to note that acupuncture and massage and moxibustion are under a different licensure. So legally we can do that, but usually we are not trained about doing acupuncture, moxibustion, or massage or things like that. And my main research interest is using real-world data to create a clinical decision support system for Kanpo medicine, and especially for traditional herbal medicines and traditional herbal preparations. And I'm also working with other two, but they are not for today's my talk. But I am also working with a genetic background of cold temperature hypersensitivity and licorice-induced pseudo-hyperaldosteronism. And on a personal note, I love my family, and I am a big fan of Korean food, including Korean barbecue, kimchi, makgeolli, jingo, chansu, or something like that. All of them are very popular in Japan, and I'm so happy to be here in Korea. Locally, I don't have to mention about it, right? Okay, so now let's move to the main topic of Kanpo's role, traditional Japanese medicine role in Japan. Kanpo is a unique adaptation of ancient Chinese medicine. It is covered by our national health insurance system, and about 90% of Japanese physicians, biomedicine trained Japanese physicians use Kanpo medicines in their daily practice. However, only less than 1% of Japanese physicians is specialist of Kanpo medicines. So yeah, I am kind of outlier of doing Kanpo medicine, specializing Kanpo medicine in Japan. And it is also widely available as over-the-counter drugs. The herbal preparations are available as over-the-counter drugs. So pharmacists also play a key role. And the situation for pharmacists is similar to that for physicians. So, there are no Kanpo-only pharmacy schools in Japan. And even though they learn about medicinal plants in their standard curriculum, and Kanpo is included in their national exams, but still, Kanpo specialized pharmacists are very much small number in Japan, and training opportunity is kind of limited in Japan. So because both non-specialist doctors and pharmacists handle Kanpo products, herbal products, and the diagnosis often depends on their very limited personal experience or limited anecdote. Furthermore, the number of Kanpo specialists is gradually decreasing in Japan, so this situation highlights a strong need for standardization of practice and better educational tools in Japan. Therefore, our goal is to use AI and big data to translate this anecdote-based knowledge, specialist anecdote-based knowledge into more objective, data-driven algorithms that is easier for use to application by the non-specialist physicians or pharmacists. This is a key theme of my talk, from anecdote to algorithm. This is the outline of my presentation. First, the background of Kanpo medicine, as I mentioned, and second, our method. Third, our result, and finally, my conclusion. So let's start with our methods. We have built a large-scale clinical database over more than 10 years, and actually 15 years. And the data comes from 6 representative Kanpo medicine centers across Japan, from the northern part of Japan to the south island of Japan, near Korean Peninsula. And this database includes patients' symptom questionnaires and diagnosis based on modern medicine, ICD-10 code, and the traditional patterns, ICD-11 code, and the Kanpo formulas that were prescribed by the specialist physicians. Next, our analytical approach. We applied machine learning to find the relationships between patients' symptoms and the diagnosis made by expert physicians, Kanpo expert physicians. And let me briefly explain the model we use. It's a type of machine learning called a random forest. You can imagine it as a collection of many simple, smaller decision trees, not one single huge one. And each tree makes a decision based on a patient's symptoms. And for example, a symptom sends the data down one path or another, like that. And at the end of the path is a diagnosis, such as A or B pattern diagnosis. And this single diagnosis counts as one vote by one small vote. And we use 500 of these trees, and they all vote. All 3 votes have one vote, and the final prediction is decided by the majority vote. A key strength of this model is that the symptoms at each branching point, named as node, are selected randomly. So this method is very robust and helps to prevent overfitting. We also used actually natural language processing. We used NLP to develop drug information systems. However, with the recent emergence of large language models like ChatGPT or Gemini, the landscape in this area has changed dramatically in this 1 or 2 weeks, or maybe in some months. So I will not go into detail on this specific topic today. Instead, I'd like to add one more thing about one future direction using these new technologies. Until now, we have focused on collecting data in a structured format for 15 years. But now we are exploring whether we can directly analyze the free text descriptions in electronic health records, as Dr. Shin explained in the morning lectures. Unlike in Korea, Japan does not have a nationally standardized format for electronic health records. Data formats differ between vendors, which has made it difficult to integrate data. However, we believe that LLMs have the potential to overcome this issue and help us integrate EHR data from multiple institutions all over Japan. Right, so next I will show you our results. Here are main results, and actually one of our results. And we developed prediction models for three fundamental Kanpo pattern diagnosis. They are deficiency excess, cold heat, and Qi stagnation from Qi blood flow pattern diagnosis. As you can see, the prediction accuracy was not so bad, not quite good maybe. And for example, the accuracy for deficiency excess was about 81%, and for Qi stagnation, it was 96% in a selected patient group. Actually, for deficiency excess pattern and cold heat pattern, the accuracy could be over the 90% in selected populations, and around 80% accuracy is kind of real-world evaluation data. And these models can classify our patient's condition with high accuracy using only the reported symptoms without kind of physical examinations or lab data or something like that. To give you a visual example, this figure shows the result for our Qi stagnation model. And let me explain the figure. The vertical axis shows the probability of Qi stagnation predicted by our machine learning model. The top value, 1.00, means 100% probability, or as I said, all 500 votes predicting Qi stagnation for this data or for this patient. The bottom is 0. The horizontal axis shows the patients sorted by their prediction value into two groups. Those diagnosed with Qi stagnation and those who were not. Each dot represents a single patient from our test data. As you can see, the two groups are separated very cleanly. The patients who were actually diagnosed with Qi stagnation by specialist physicians, the top cluster, received very high prediction scores from our model. And in contrast, the patients without Qi stagnation, the bottom cluster, received very, very low scores. This demonstrates that our model can effectively distinguish between patients with and without this traditional pattern based on their symptoms. This table shows the top 10 most important questionnaire items that our model identified for making its predictions. I hope you can read the characters. And let's look at the cold heat pattern on the right. As you can see, subjective patient sensations like cold hypersensitivity in legs, cold intolerance, cold hypersensitivity in hands, general cold hypersensitivity have a high importance. This is clinically very intuitive. I'd like to clarify that importance here in the table means, and the table is sorted by this value, the importance, and it's not a simple weight, and instead importance is calculated by measuring how much the model's predictive performance will worsen if that specific item were removed from the model. The logic is completely different from that of linear regression models. And there are two critical takeaways from this. First, these items identified by the model are consistent with the diagnostic criteria for deficiency excess and cold heat patterns in the ICD-11 definitions. And this helps validate our model from a clinical perspective. And the second, we searched for biological, we searched a biological basis for these subjective feelings, especially for cold heat pattern. And we conducted a genome-wide association study on patients with and without hiesho, which is Japanese for cold temperature hypersensitivity. Our study identified multiple gene variants related to patients that are involved in the threshold of subjective temperature sensation. This is a key findings, and it suggests that there are objective genetic variants that supports the subjective patient's symptoms or informations, the patient's own feelings, which is a crucial part of traditional medical diagnosis. Based on our diagnostic models, we are developing a clinical application. A patient can input their symptoms using a tablet, and our system visualizes the patient's condition based on our prediction models. And this can help doctors, physicians, especially non-specialists, in their decision-making process. However, moving from diagnosis to predicting the final prescription is a much more challenging task for us right now. And the difficulty is that prescriptions are more often not exclusive to a single diagnosis. Furthermore, similar formulas create clusters, and interchangeable herbs result in a very high dimensional space for the data. So this makes it difficult to set a clear target for the prediction model. We are currently conducting an exploratory analysis to understand in which situations prediction works well and where it fails. By doing this, we are preparing to build a reliable prescription prediction model in the near future. We know that many researchers in Korea and China are pioneers in this area, so we are very eager to learn from your expertise. Right, so now I would like to move on to the conclusion. In conclusion, our AI-supported strategy does not replace physicians, but augments them with data-driven insights. This is very important for the many non-specialist physicians who come for preparations in Japan. We also believe this approach has great potential as a global educational tool. It can help doctors, physicians trained in Western medicine to understand the complexities of East Asian medicine. Finally, our from anecdote to algorithm approach is a Japanese contribution to the global effort to modernize traditional medicine. We hope to continue this international dialogue and work together for a sustainable future for traditional medicine. So I would like to express my sincere gratitude to all my collaborators for this project. This work would not have been possible without the support of many people from Keio University, the University of Tokyo, and other great institutions. I also want to thank the funding agencies for their generous support. Right. Thank you very much for your attention.
Thank you, Professor Tatsuro Yoshino. It was an inspiring lecture showing how AI and big data reshaping traditional Japanese medicine and the future of healthcare. 네, 그럼 계속해서 다음 세션 만나보겠습니다. 다음으로는 중의학 연구에서